lunch. When it's finished, I do have to say something important about lunch, so if I don't say anything, then remind me to. But we've got Lorenzo up next, and he's going to talk about the elliptic PDEs again.
But on the bright side, I think I will be able to deliver the talk in like 40 minutes instead of an hour, so we have extra time for lunch. So, yeah, well, is this one working? Can you hear me okay? Okay, good. Okay, thanks for being back. And I'm gonna present some work that I have been doing the last few years. It's a joint collaboration with Fabio at EPFL, with Raul and Joakim at KAUST, and with Abdul-Lateef, who was at KAUST and now is in Oxford. It's about multi-index stochastic collocation for elliptic PDEs with random data. But elliptic PDEs are just here today because of presentation purposes. I mean, there's nothing that prevents you from applying MISC to other equations. And I think that Raul is going to present other applications, perhaps in his talk in Thursday morning, I think. Okay. Also, I'm going to try to be as little technical as possible. So maybe I will not lose the statisticians. Let's see how good I am at that. So I will quickly go through the setup and notation of UQ, but just because I want to set the notation, not that I need to explain UQ to any of you guys. I'm gonna try to sell the idea of this multi-index stochastic collocation and give you a first bunch of numerical tests to show that it's a promising technique. Then I'm gonna go back to theory and introduce this thing called isogeometric solvers, which are, you will see, but are pretty useful in this context. Some additional numerical results, and then wrap up a conclusion. So, okay, throughout my slides, the mathematical model is an equation P equals 0, and the solution is U, and X are spatial variables, so the spatial domain. And then, of course, because this is a UQ talk, parameters comes in. So my solution is a function not only of the spatial variables, X, but also a solution of a bunch of parameters, Y, that are supposed to be, of course, random. Otherwise, I wouldn't be standing here. And they are random for whatever reason. And, of course, I can collect them in a random vector. In my talk, capital N denotes the number of components of this random vector. So I'm dealing with capital N random parameters. And as a consequence, U is a random function. It's an implicit random function because I don't know its analytic expression. I know the values of U of Y only through a PDE solver. So I feed my PDE solver with a bunch of parameters. I compute the PDE, and I get out a solution U, which I'm interested in. And I'm actually interested in computing the expected value of U, the variance, the probability that U exceeds some threshold, and stuff like that. The working example for this presentation is the famous elliptic PDE. So here, this one. Capital B in my talk denotes the physical domain, and it could be either in 1, 2, or 3 dimensions. Small d is the physical dimension. And for the time being, let's say that I'm interested in evaluating U, my solution U, at some point at X. It will be other also quantities of interest, but for the time being, let's suppose that I'm interested in knowing the value of the solution of the PDE at some point in the domain X, in the domain B. Now, of course, the random parameters comes in, and in particular, I'm assuming that the diffusion coefficient here is depending on a bunch of random parameters. And as a consequence, also U depends on these random parameters. And I'm interested in computing, say, the expected value of my solution in this point x hat. And again, I have n capital independent variables. In addition to what I said before, now these random variables are uniformly distributed and independent in -1, 1. Okay? So the two issues that we have to face are, first of all, capital N can be very large, and I will tell you why in a second. And second, because N can be very large, that is challenging computationally. So I want to know which is the cheapest discretization to achieve a given tolerance in the spirit of the questions that have been made before. Okay? So I need to discretize the PDE with a certain mesh size. I want to use the coarsest mesh size that allows me to get to a certain tolerance in the value of the final outcome, that would be the expected value of u at this point x hat. Now, how come n can be large, and how come I'm concerned about mesh sizes? The thing is that the random field here, A, is possibly quite rough. So these are random realizations of a unit of a random field in 1D. So in this case here, capital B, the physical domain, is 1D, and each line colorlines a realization. And my expression for the random field is this one. So it's a sum of oscillation phi k who have random amplitude, because the phi k are normalized per se, but they are multiplied by some coefficients gamma k that go to 0 as k increases, and further multiplied by these random variables yk. So and the frequency of oscillations of the phi k increase as k increases. So few k's are sufficient to describe things like this, but if I want to describe things like this, rougher and rougher, I need more and more random variables, because one variable comes with one frequency. So if I need to obtain this thing as a superposition of many, say, sine and cosine, I need many frequencies. Hence, I need many random variables on the one hand, and a very fine mesh in physical space on the other hand to deal with this. Okay? So I have a problem which is potentially quite complicated, both because I have many random variables and because I need very fine meshes. So how do I deal with this? It's the idea of the multi-index stochastic collocation. Well, the naive way to do UQ here would be Monte Carlo. I don't need to tell you what Monte Carlo is, but this is just to show the pictures. For each point in this sampling of the random variables y, each point in this random sample is a realization of the random field. I plug the random field into my equation, I solve the PDE, and I get the number, and then I take the average of the numbers that I got. And this sketch here is just a picture of one possible domain, physical domain, that I might want to solve my PDE in. Okay? So you see here there's a physical mesh with a certain mesh size, and you see here a bunch of points in this hypercube that will correspond to a bunch of realization of my random field. Okay. Of course, this is low, so you want to do something better than this. And the alternative would be to use a structured grid in the parameter space. So when I say, I will often say parameter space, which to me is interchangeable with random space. The random variables to me are random parameters. I can use random variable or random parameter interchangeably as two words, okay? But they are the same thing. So again, I have to cover the random space or the parameter space, which is an hypercube. And instead of covering it with a Monte Carlo sampling like this, I cover it with a structured grid like this. But then the thing goes up the same. So for each point corresponds to a different realization of a random field. I plug the random field in the PDE, I solve the PDE, I get a number, and I take the average of the numbers that I got. Okay? So just two different ways of covering the random space, but eventually the procedure is the same. I have to solve a bunch of PDEs. And this is more accurate, but it's expensive in the sense that if I want to cover an hypercube in capital N dimension with a structured grid, the number of points in the grid is exponentially in the number of dimensions. And if I have to use many random variables, this number, the points will explode, okay? So far so good? Probably, okay. And that's where the multi-index stochastic collocation comes in. It's closely related to sparse grids, so that adds to the discussion we had last week. So I'm gonna try to be informative but not technical. So to begin with, let's consider a problem with one random variable and in physical domain in d equal 1, so a PD on a line with one random variable. And suppose I want to use stochastic collocation probability, meaning I want to choose a structured grid for each point, solve the PDE, and get the numbers. And let me call G sub alpha m the number that I get out of this procedure, okay? In particular, I'm using two subscripts here. The first subscript is alpha and denotes the level of discretization in space. It's an integer, 1, 2, 3, that tells me the discretization level. In particular, I have 2 power alpha elements in my physical mesh in space. And capital and little m is the number of collocation points in probability, okay? So I need to solve small m PDEs on a mesh of 2 power alpha elements to get my algorithm going. And then beside this discretization, I introduce 3 more, so 4 discretizations in total. The one that I just told you about, the coarsest one. Then I have 2 intermediate ones. One is a discretization I call G beta m. It has the same number of points in probability, small m, but I'm increasing the discretization level in space. So I'm using 2 power beta instead of 2 power alpha elements in the physical mesh, okay? I'm solving the PDE with a finer mesh than before. Then I'm considering the dual approach in which I keep fixed the number of elements in the physical mesh, but I increase the number of points in probability from little m to larger m, okay? So I'm solving, going from the first one to the third one, I'm solving more PDEs on the same grid, while if I go from the first one to the second one, I solve the same number of PDEs, but on a finer grid in space, okay? And then ideally, I would like to do both things. So I would like to solve more PDEs on a finer grid to get a more precise approximation. This would be our ideal goal, but in our thinking, this is too expensive to be done, okay? I cannot afford to improve the approximation simultaneously both in space and in probability, okay? Because it is too expensive. So this is the trick of sparse grids in a nutshell, super nutshell. So let me start by rewriting this telescopic equality here, okay? My goal would be G beta m. I rewrite it on the right-hand side of the equality, and I add and subtract all the partial grids that I talked about, okay? And then I rearrange this expression. And out of rearranging this expression, you see that I have put in evidence three corrections, if you want. One correction is a correction in space only, so it's a difference between the two solutions that I get by increasing the spatial discretization only. I have the dual correction, which is the correction in probability only, the difference between two consecutive approximations refined in probability only, and then whatever is left, let me call it mixed correction. And let me rewrite it this way, where you see here I have delta for correction, 1, 0 is first direction, so space, 0, 1 is second direction, so probability, and 1, 1 is mixed correction. And in essence, this is a hierarchical decomposition, and the idea here for the idea of sparse grids is that I assume, or actually have way to show that the mixed correction is way smaller as a contribution to the approximation of the other corrections, okay? So ideally, if I drop this mixed correction, I don't lose much in the approximation, okay? But on the other hand, if you remember, this mixed correction is the only one that involves my target, the G beta M. So it's the only one that includes computing the fine approximation in both directions. So it's the most expensive, but under certain say assumption, it doesn't add much. It costs a lot, but it doesn't add much to the approximation. So I'm safe to say that if I drop it, I save a lot in time, and I don't lose much in accuracy. Then I expand back those two corrections to what it was. I do some algebra, and I end up with this formula here. So I wanted to compute this, but this is too expensive to compute. So instead of computing this, I compute these three things here. The three coarser or intermediate approximations, okay? It's a way of combining these three coarse approximations in such a way that my result is approximately the ideally fine discretization that I cannot afford to compute, okay? And this was for a very simple PDE with one random variable and in one in dimension 1 in space. And if you have more than one random variable and or more than one physical direction, what you do is the same. So you would say you have two random variables and a problem in physical domain dimension 2. You will need to specify two mesh sizes and the number of and a grid with, say, m capital points in the first random variable and m capital points in the second variable. And again, you rewrite your ideal goal as a sum of corrections, partial corrections, where you increase one discretization parameter only. So either you increase only one physical discretization or the other, or you add points in one random variable or the other. Then again, you will all the mixed corrections. You will know that the mixed corrections are not all equally important. You will drop the non-important corrections. You will end up with a linear combination of many coarse approximations, okay? So this is in spirit the same idea. You want to compute a fine approximation that you cannot afford. Instead of that, you compute many small approximations, and then there's a formula that tells you how to combine those coarse approximations together, okay? So again, it means that I'm never assembling the refined grid in space in all directions. I'm always considering partially refined grids. So either, say, if I want this, if this is my domain in space, I never simultaneously refine all the three dimensions, but say I might say, I refine only through thickness, or only through radial, or only through angular directions, okay? I never refine the three dimensions together. And at the same time, I never cover the random space with a equally refined grid. That I don't do. Either I increase approximation along the first random variable only, or along the second random variable only, okay? And then combined together, I will never solve the PDE for these many points, but I will say, I will consider discrete improbability. For each of these points, I will assemble the random field and solve the PDE, but on this anisotropic grid. Then I will do the same on another grid improbability combined with another grid in space, which is a different discretization than before. Then I might consider a third grid improbability with the same mesh. But all of this, the key point here is this: none of this is fully refined in all the direction in space and in all the random variables in probability, okay? And so that's the idea of sparse grids in a nutshell, or actually the idea of MISC, of multi-index stochastic collocation. It's called multi-index because you have to prescribe simultaneously how to refine many directions, be it a physical direction or a random direction. But in essence, I like to think that this is in spirit an extrapolation. So it's a way to combine many coarse approximations in such a way that you end up with something which is close to a refined approximation. And the spirit is you never refine all directions simultaneously. Crucially, if the choice of these corrections is done appropriately, you are automatically balancing the error in space and in probability, because you have the freedom to choose, okay, should I refine more in space or should I refine more in probability, okay? Or which direction in space is more important to refine, or which random direction is more important to refine. So I never, because I never do this simultaneously in more directions. So if I'm able to estimate this properly, then I'm automatically balancing out the physical and the probabilistic approximation errors. It is a sampling approach, so it's, in the end I will have to solve a bunch of PDEs on different grids, but it's very amenable to parallel computation, because it's inherently a sampling approach. And it's, crucially, this works well if you have a tensorized solver in space for the numerical analysts here. You cannot just use a simple finite elements on a triangulation, because even if you prescribe I have 10 elements in this direction and 20 in the other one, then the triangulation mixes everything together. You need to be able to keep directions separated in the solving, okay? So it works for isogeometric, finite differences, finite volumes, spectral elements, finite elements on quad meshes. It just doesn't work well for FEM on triangular meshes, okay? So your spatial solver needs to be adapted. And okay, I will tell you more on IGA later on. This is just a formula to show that I can, that I have ways of computing a priori the corrections to consider in my MISC approximation. If you don't want to do that, then we also have adaptive algorithms. So you start from the coarsest approximation, you add the two corrections, say the correction in space is in this direction and the correction in probability is in the other direction. Then suppose that somehow I get to know that the correction in probability was more important, more effective to be added, and then I will add the further correction in probability. But if instead, if I find out that now at this point it's more important to further correct in space, so to refine in space, I will do that. Then I have 3 more candidates, say that this is the most important, I keep going and keep going, okay? So you don't need to know in advance which are the corrections that you need to add to your 0 approximation. There are algorithms that tell you which are the most appropriate corrections to be added as the machinery goes. And this is, of course, if you know something about your PDE, it helps in choosing the set of corrections to be added, but this is very general, and in principle can be applied to whatever PDE you might want to have, okay? And it's not even restricted to be space and probability. It could be space, time, and probability, or space and number of particles and probability, or space and whatever, okay? It's a very general way of thinking of decomposing a tensor approximation into a sequence of corrections, breaking up the exponential cost of the tensor structure, okay? We do have convergence theorems here. They come in different flavors depending on whether you have a finite or an infinite number of random variables. In particular, in the finite, if you have only a finite number of random variables, there will be a log term correction here in the error estimate. If you have instead an infinite number of random variables, that log term disappears and you're left with this error estimate. Now this sounds sketchy. I do have more precise slides with theorems properly stated, but in the interest of time, I think I'm gonna just skip and we can come back here later if you want. I'd rather show some numerical tests to convince you that this thing is actually efficient. So just to recap, I'm solving this PDE with a random diffusion coefficient who has this expression, so a sum of more and more rapidly oscillating function phi k with a random amplitude. The random variables are uniformly distributed, and now I'm computing again with the MISC and a bunch of other methods. So this is a big result for us. It shows a bunch of methods, and the one that the MISC method that we are proposing is performing the best. So this is a PDE with 20 random variables, a smooth random field, and these are the details of the simulations. They are not that crucial at the moment. You see here there's a whole bunch of lines. This represents the convergence of the error as the computational work increases. And the dotted line is the theoretical work error estimate, and you see that our method is either the blue or the orange line, depending whether you choose a priori or a posteriori the set of corrections to be included in your approximation. They're both doing fine. They're both following the expected convergence rate, and they are doing significantly better than the alternatives. The alternatives being either a less efficient way of prescribing the corrections because you don't know exactly the way that the size of the correction are properly estimated, or because you consider only uniformly grid in space, so when you always refine all direction in space simultaneously, or because you are using Monte Carlo, which is a suboptimal estimate in probability, or so. Okay, so there's a bunch of alternatives, but let's say the MISC is the one that is most effective, at least in this scenario. This is a different test where we have now an infinite number of random variables. So before it was just 20 random variables and three-dimensional problem in space. Now it's again three-dimensional problem in space, but with an infinite number of random variables. And here we're focusing on the convergence with respect to the smoothness of the random field. Again, our predictor correct behavior is the one that we actually see. And just to tell you that we actually never, okay, although we have an infinite number of random variables, in principle, it's not like we compute with actually an infinite number of random variables. Random variables are activated a bit after a bit. So we start with, say, 10 random variables, and then as the computation keeps going, you eventually put quadrature points in 1,000 of these random variables. The random variables are sorted by their importance, so you only add the further random variables when you need them, because they are second order or third order importance. But you never activate all of them simultaneously, so it means that you will never consider 1,000 random variables in the same shot. The sum of corrections are such that you never consider grids in probability with more than, say, 10 random variables. So you never consider 1,000 random variables in one shot. It's 10, and then another 10, and then another 10, and then another 10, okay? That's the thing that makes it feasible, okay? And then this was the first bunch of results over a pretty simple problem in practice. And now, if you want to keep going a bit further in the complexity of the PDE in space that you want to solve, so if you want to solve problems on fancy geometries or more fancy PDEs, you might want to consider replacing the standard. This was a standard multilinear finite element solver, so pretty standard. If you want to solve more fancy stuff, you might want to turn your attention to isogeometric solvers. So what are isogeometric solvers? This is the new bit for the numerical analysts, maybe. So IGA, isogeometric solvers, are a way of using, in a sentence, it's a B-splines-based PDE solver. So instead of using finite elements, you use B-splines as a basis for your PDE approximation, okay? The motivation to do this comes from the CAD world. In the usual industrial pipeline, production pipeline, there's a CAD engineer designing a piece, and he does this on a CAD program that creates a CAD geometry. And this CAD geometry is described by these B-splines polynomials, or NURBS. It's another sort of B-spline polynomials, okay? And in 2005, by 2005, let's say, it was very clear that once you have this CAD geometry, if you want to do a finite element analysis, you need to convert the CAD geometry into a FEM mesh, a FEM suitable mesh. That operation is possibly expensive and annoying and time consuming, and possibly a major bottleneck. So Tom Hughes and other guys came up with the idea of using, of jumping this step. So instead of converting the CAD geometry into a mesh suitable, a finite element suitable mesh, you try to solve the PD directly on the CAD. So there's no meshing, which saves the time of doing the mesh, and also describes exactly the domain. So if you want to compute over this domain here, the fancy one, oh, come on. This one, if you do a mesh of this, you will approximate this with a piecewise linear description. With splines, this is it. You don't have any approximation, any linear approximation, okay? So it has some advantages. And so now I should tell you why, what are these B-splines and how they come in handy in the multi-index stochastic collocation framework. So everything starts with a knot vector. So a reference domain, in this example 05, and a knot vector 0, 0, 0, 1, 2, 3, 4, 4, 5 that splits this reference domain into elements 0, 1, 1, 2, 2, 3, 3, 4, and stuff. And out of this knot vector, you generate a set of B-splines, these colored lines here. Okay? There's a recursive formula, it's called the Cox-de Boer formula. You feed this formula with this knot vector, and it delivers these polynomials. These polynomials have a certain degree, P. They have a certain continuity among the elements. So here they are C1, and here they are C0, for instance. And whether this is C0 or C1, it depends on the number of repetitions of the knots. So by playing with the repetition of the internal knots, you get to choose whether your polynomials are C0 or C1 or C2 or C whatever, okay? And also by playing with the, at the same time playing with the knots, the first one and the last one, you also prescribe the degree of the polynomials. So you have a very straightforward recipe to generate polynomials of any degree and any continuity. And then you take linear combinations of these polynomials with points pi in the physical space, like this. And out of that, you get a curve in the physical space, this thing here. I'm taking these polynomials, each polynomial is multiplied by a point p, one of those red dots here, and as c, the parametric variable, goes from 0 to 5, which is the last value of the parametric domain, I go along my curve from beginning to the end. Okay? Good. And then how do I describe surface with this? I do this by tensorization. I do tensorization of polynomials, and then I end up tensorizing these two polynomials and multiplying the product of the polynomials by a control point again. I describe not only a line, but a surface, okay? It's a parametric surface. And because this is tensor, this is why it comes in well with the MISC, because I told you I need a tensor solver, and this is a tensor thing, okay? And the surfaces need not be planar, they can be whatever. And if I keep further tensorizing, I get volumes, okay? So I have a nice way to describe non-planar surfaces and volumes. And once I have those basis functions and those surfaces, I can solve the PDE with them, okay? And in particular, because I have high order and I have high continuity, it's very easy for me to solve, for instance, B Laplacians or P Laplacians or PDEs on surfaces, okay? B Laplacians are useful, for instance, because they describe the plate bending equations, for instance. So they are useful in engineering. They have some, there's no free lunch, of course. They come with issues that I'm not dwelling into. But to me, this is very useful because it's a tensor method. It's a very easy way to deal with a tensor method of a fancy geometry. So I'm going to use it for my purpose of the MISC, okay? So instead of doing multi-index stochastic collocation with multilinear finite elements, I'm doing multi-index stochastic collocation with IGA solvers, okay? So in this example here, I'm solving a PDE in this domain, this thick quarter of annulus, which is the IGA equivalent of a cube. Anything that, before you can publish anything, it has to work on this. This is the thick quarter of annulus is the new cube, in a sense, for IGA. Because we have this fancy domain, we consider this fancy diffusion coefficient, which evolves mostly along the angular direction. Okay. It's not that complicated. It's just a superposition of 3 oscillations, so 3 random variables. It's pretty cooked up as an example, but it shows my point. That's this one here, that if I want to do multi-index stochastic collocation with this structure, I can. And because I'm using a B-splines of continuity 2 and degree 3, it's very effective in the space part. So I'm no longer bounded to use multilinear finite elements. I can increase easily the degree, and I get a significant advantage in computational time with respect to multi-level Monte Carlo or Monte Carlo, blah, blah, blah. And I can do even more fun stuff. I can solve, for instance, the vector elliptic PDE. That would be the elastic equation over this shape here, this horseshoe shape. Imagine that I don't know exactly the value of the Poisson ratio and of the Young modulus, which are the 2 constitutive parameters of the response of this thing to pushing and pulling. So imagine this is a generalized Hooke law for pushing and pulling this metal object. If I don't know exactly the elastic constants, these 2 numbers, I want to do, in this case, uncertainty quantification in the displacement of the red dot here, okay? So I want to know the expected elongation of this thing subject to pushing and pulling, given that I don't have exact values for the elasticity constants, okay? Again, the IGA allows me to be very efficient here in representing this geometry exactly and in using a high order PDE solver. In this example, I'm using these random distributions, which are actually, they're coming for an industrial oriented application. These are standard variability ranges for titanium. So it's not like titanium. You might think, okay, we know everything about titanium. We don't. We have these bounds here depending on where you go and read. Okay? And again, we did run this. We did run the multi-index stochastic collocation over this problem. This is the convergence that we got. It's pretty flat, which is great. It means that we can go to pretty small tolerances in pretty decent computational times. And I'm in conclusions, so yeah, 40 minutes. Yeah. And so multi-index stochastic collocation, if you want, is a very generic machinery that allows you to prescribe the coarsest discretization that allows you to reach a certain tolerance in your computation by playing with univariate corrections. So be it that you decide to refine along one physical direction or to refine along one random direction, you have a way of prescribing this one at a time corrections that would be one at a time improvements or one at a time refinements in such a way that you balance your error among the different directions in space and direction in probability. You can do this a priori or you can do this adaptively by an algorithm. You can auto-balance the different sources of error. It needs a PDE solver with a tensor structure to be fully effective. We do have estimates available, and as a byproduct, if you now think that, this is again for the numerical analysts, if you freeze the random variables and only think of PDE in space, this is IGA sparse grid approach to solve a PDE. Okay? And it improves the standard sparse grid machinery to solve PDEs in the sense that it's pretty straightforward to deal with high degree / high continuity polynomial basis. And you can easily go to generic domains without fancy hyper stuff for mapping. And finally, advertisement for this workshop, which is going to happen in Pavia in the late summer or beginning of the fall, take it as you want. And it's a workshop on UQ focusing on subsurface environments. If you don't know where Pavia is, it's here. It's like 30 kilometers south of Milan, if you don't know. So it's pretty easy to reach. We have a whole lineup of invited speakers, pretty impressive. And it's a mixture of mathematicians and statisticians and engineers. We will talk about hydrology, geology, biogeochemistry, CO2 sequestration, so everything that has to deal with UQ in subsurface. These are pretty pictures from Pavia. It's not always that pretty, but okay. Someone knows what I'm talking about. And registration will open soon. Some abstract submission will open soon, so feel free to join us. I'm leaving you here with references, and thank you for your attention.
Right, thank you. Fabio, then sorry, Lorenzo. But I just want to point out why I mentioned elliptic PDEs at the start. It's really important, I think, in this mixed audience that we have this sort of base example that we can all sort of latch onto and understand. So it was a positive comment.
Yeah, no worries. No worries. No offense taken, really.
And thank you for keeping to time. So any questions now? We've got, well, quite a while now for questions. So, Catherine?
Can you say a bit more about the adaptive part? So in the results that you showed where you said you were learning N and you didn't fix N before you start, had some results with, you said with a posteriori error estimation.
It's the standard Gerster-Gribel approach, in essence.
You had a very specific quantity of interest. Is this fully flexible if I change my quantity of interest?
Yeah, well, we had we are not restricted to a single quantity of interest. I mean, you can, as long as they are functional, it is pretty straightforward. Plus, this is an approach. In this talk, I focused on computing expected values of those quantities of interest. So in practice, it's just taking differences between consecutive approximation of that expected value. So it's difference between real numbers. So it's really the Gerster-Gribel. You add the delta, you add the delta, take the difference, and then choose the delta which gave you the largest improvement in that difference. You might want to tweak it if you want to use, for instance, interpolation. Then but it's nothing fancy actually. It's the usual stuff.
You just said the whole theory you presented was about computing expectations. What about variances?
Well, first of all, this is not for expectations, strictly it's for integrals. So a variance is just a second moment, it works just as well. And you can even go further in using non-quadrature based quantities. I guess Fabio has a work on function approximation for multi-index function approximation, right? I saw a talk by Sebastian. Well, whatever. Yeah, it can be extended anyways. Huh? It was Monte Carlo, okay. Anyways, it can be extended to non-quadrature quantities of interest. You have to do some tweaks. We can talk offline.
In a nutshell, you're treating the spatial variables and the parameter variables by stochastic collocation, sparse collocation. So you didn't say this, but you're going to need much more regularity in the spatial variables in order for the collocation to get the...
We're not doing collocation in space. We're not doing collocation in space.
Well, the sparsification, the differencing.
Yes. Yeah. Still, it's not a collocation. it's
Hierarchical approximation.
yes, but because I'm using the combination technique, I don't need the basis to be hierarchical. I can reuse as a black box my PDE, my previous PDE solver. So of course I need mixed regularity there. Yes. So this works as long as you have sufficient mixed regularities among the x and the y's. But it's not much different than the usual, I would say. What is your question again?
Well, usually if you do a standard finite element discretization in space, you're going to have different variational spaces and different regularity. Then I'm just saying that you'll have a particular mixed regularity requirement for the spatial problem.
Yes, of course.
To work.
Yes, you need extra. Yeah, you need your function in space. I mean, for each realization, it's not enough that it is in a standard HK. It has to be in HK mix. Yes, and then further, it has to be H mix not only with respect to space, but also in the cross combination between space and probability. So that adds further on to the requests on the regularity. Yeah. So it works for as long as you have that mixed regularity across everything, because in practice I'm treating all the variables with this combination approach. So everything has to be mixed regular with everything essentially. Yes. So it's quite a strong requirement. Yes, it is true.
Anybody else? Yep.
So one thing that is still a bit unclear for me is, so you have basically mesh or grid in space and in probability space.
Mm-hmm.
How they combine, like how is that selection going on? Okay, that's some error estimate, I guess.
Mm-hmm.
But so if you change the quantity of interest, would you get different combinations?
Well, yes and no. I mean, if you do this a posteriori, then you let the algorithm discover the right corrections, then yes, you probably end up with different combination of grids in space and grids in probability. If you do things entirely a priori based on the structure of the PDE itself, it's not a given. I mean, if your solution in space has a certain regularity and in probability has a certain regularity, the one I was talking about earlier, then in a sense all linear functionals have the same, all linear functionals of the solution have the same regularity, so you will probably end up with the same set of corrections for those functionals. But it's not that obvious. So perhaps there are minor deviations, but with a single shot you can probably come up with a good set for many quantities of interest. But that is really problem dependent. So this is just a general regular rule of thumb, let's say.
So there's a lot of work on the sensitivity analysis. So do you use, when you decide to sample more densely in a particular dimension, or have your sparser within one dimension, do you use some sensitivity measures to
we
assess
might.
that or not?
We might. So if we do this completely a priori, I showed you, okay, I should go further down into the backup slides now. The a priori approach is based on a priori estimates on these, the a priori approach where I prescribe a priori, which is the set of corrections, is based on certain assumptions on the decay of the error contribution of each correction. So I'm able, under certain circumstances, I'm able to estimate a priori how much will the approximation improve if I add a certain correction. And how much this will improve depends on this, it depends on a bunch of scalar quantities, a bunch of parameters alpha and beta, these G's and these R. The R are for the deterministic part and usually are standard from the finite element books. The G here instead, if you want, you can interpret them as sensitivities with respect to each random parameter. Now you can estimate them a priori, and this relates to the size of the analytic extensions that Chris Schwab was mentioning yesterday. You can also do some preliminary computation and estimate those G's, you can also use the Sobol indices. Usually they relate, but of course if you do the Sobol indices, then you have to do some computation first and then infer. So, but yeah, in principle they are related to the sensitivities, yes.
Anybody else? Okay, well, given it's lunchtime, I won't keep you.
Yeah, sure.
Just wanted to say that whilst any discussion should probably go straight to the queue, we are extending lunch by 15 minutes. So if you could be back here at 1:45, ready for the next talk, that would be great. And thank you, Lorenzo.